So someone asked, what about the lone pairs? Lots of molecules have lone pairs on the central atom. When we have lone pairs, then we end up with two different types of geometry. We have the electron geometry, which is how the electron groups are arranged. And then we have the molecular geometry, which is the shape of the atoms, the arrangement of the atoms. If we have no lone pairs, those two geometries are the same. So consider ammonia. Ammonia's Lewis structure looks like this. And so well, that's kind of messy. There are 4 groups. Okay, come on. There are 4 groups around the central atom. 3 bonds and a lone pair. Well, that's 4 groups. How do 4 groups get away from each other? Tetrahedron. So they're going to make a tetrahedron kind of like this. So 3 of those are single bond electron groups and 1 is a lone pair. So the electron geometry, the geometry of the electron pairs is tetrahedral. To get the molecular geometry, we're going to imagine that this balloon is invisible. It's not that we popped it and it's gone. It's there. It's repulsive. It's causing these other guys to be closer to each other than they'd like. But it's invisible. So if we make that invisible, we have something that looks like this. So here I've got a model of that, and so this would be the lone pair on top. And when we're looking at molecular geometry, electrons are too small to see. Atoms are too, but relatively speaking. We're just looking at the atoms. And so we need a name for this thing. It's a triangle, but it's not flat. So this is called a trigonal pyramid, because it's not flat. So, trigonal pyramid.
Is that going to happen with any lone pair?
Yeah, the lone pairs are going to be invisible balloons. So we count the electron groups, and we think about what would that many balloons do. And then if we have lone pairs, we make those balloons invisible, and the molecular geometry is what we've got left.
So in a test, you can ask for both, right? You can ask.
Yeah. You could be asked for both electron and molecular geometry. You could be asked for one or the other. So lone pairs are more repulsive than single bonds, than any bonding pairs, actually, because they spread out in space. And here's an illustration to help us visualize why. So if we have a bonding pair is stuck between 2 nuclei. And so it's constrained. A lone pair is, basically attached to the nucleus, but there's nothing on the other side, and so it can just spread out and get really big and fat like that. So that's going to take up more space. So when we look at ammonia, the ideal tetrahedral geometry would be 109.5 degree angles, but this lone pair is more repulsive, and so the hydrogens are like, well, I hate you, fellow hydrogens, but I hate the lone pair more, and so let's get a little closer together.
Are lone pairs more repulsive than single or triple bonds?
Yes. Lone pairs are the most repulsive. They take up the most space. So again, I do not want you to try to memorize that the bond angle for ammonia is 107. But you should be able to tell me that it's less than 109.5. Because this guy is pushing those guys away. So these guys have to get closer together. This angle, right with a white marker, that doesn't work. This angle is greater than 109.5. And this one is less than 109.5. Any questions? Oops. Let's look at the Lewis structure for water. So looking at the oxygen in the middle, how many groups? 4. A lone pair is a group, and a single bond is a group. We have 2 of each, so 4 groups. What do 4 balloons do? Make a tetrahedron. So here, this is going to make a tetrahedron, but now 2 of the balloons are invisible. So here's my tetrahedron, and I made 2 of those invisible, the lone pairs. And so what is that called? That's our bent structure. It does kind of look like Mickey Mouse, but it's bent. So we have these really fancy names like trigonobipyramidal, like really hard to pronounce, and then this guy is bent, right? We should just be thankful, right? If all of those were bonds, the ideal geometry would be 109.5 degree angles, but these lone pairs are more repulsive. And there's 2 of those now instead of 1 on the ammonia, and so these single bonds are going to get pushed even closer together than they did in ammonia. So relative repulsion of electron groups. Lone pairs to other lone pairs is the biggest repulsion. Lone pairs to any bonding pairs is the next biggest. And then bonding pairs to bonding pairs are the smallest repulsion. So the number of lone pairs affects the bond angles. Here we have no lone pairs, 1 lone pair, 2 lone pairs.
So the more lone pairs, the smaller the angle.
Yep, the more lone pairs, the smaller the angle. So what's the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair?
If it has 1 lone pair, it's gonna end up having 2, so then, no.
Yeah, so trigonal pyramid is the correct answer. So, you can draw this on paper, you can draw it on the whiteboard in your mind. And if you don't have one, you should get one. They don't cost very much. And the markers never run out of ink. So central atom, it says 3 bonding groups and a lone pair. So that's a total of 4 groups. Tetrahedron. One of the balloons is invisible. So we have that triangle that's not flat, trigonal pyramid. Yeah, so trigonal pyramid is a noun, and trigonal pyramidal is an adjective. Yeah, they mean the same thing. So, and actually, to be consistent, this should be AL there, because linear, planar, tetrahedral, that should be. Yeah, bad grammar on the slide. I am not going to make you spell these words or pronounce them for points, okay? So on a worksheet or something, as long as I can tell which one you mean, good enough. On exams, these will be multiple choice type questions. So it would be like this, and you pick the correct one, okay? So you should know that trigonal planar is flat. Trigonal pyramid is the one that's not flat, okay? 5 electron groups with lone pairs. So now I have to switch my model, kit model here. I can't do this with the balloons because I haven't figured out how to make a balloon just go invisible yet. Maybe that'll work out at some point in the future. structure. This is the one I need. Yeah. I mean, I could make them disappear by popping them. But, yeah. But then the shape would change. Okay, so I'm making a trigonal bipyramid with my model kit here, ball and stick models. So this is asking us to draw the Lewis structure for SF4. You always need the Lewis structure because if you just look at the formula, you might think, well, this has 4 bonds. It's got 4 fluorines, right? No. Come on. So if we do our electrons, those guys are a little disconnected. There's a lone pair on the central atom. You only know that if you draw the Lewis structure, count up all the electrons, do all that whole thing. So we've got 5 groups. 5 groups is the trigonal bipyramid, little girl with the skimpy tutu. So what's tricky about this guy is that not all the bond angles are the same. And so it matters which one you make invisible. Up until now, it hasn't mattered. So there are axial and equatorial groups. Lone pairs take up a lot of space. They're really repulsive. They are going to go where there is the most space. So if it was in the axial position, it would have 3 90-degree repulsions with bonding pairs. Here, it's going to have 2 90-degree, and then these are 120, which is much bigger. So it's got more space. So the lone pair is going to be on the central atom. So I'm making that invisible. No, I didn't. I pulled it off, but we can pretend. I made that invisible. Magic. And what do we call this? Seesaw. Okay, seesaw. So again, we've just gone into the kind of ridiculously simple names. We have bent and seesaw. What if we have another lone pair with our 5 groups? So here we've got bromine trifluoride. This has 2 lone pairs, 3 bonds. So again, 5 groups, 5 balloons, trigonal bipyramid, make 2 of them invisible. It needs to be the equatorial ones, the ones around the middle. Maybe you could think of it this way too. The ballerina's losing part of her skirt. She's not losing her head. Because the other way, you'd be chopping her head and her feet off. It's much better to lose part of the tutu because she's got a bodysuit on. She's not even going to be naked. It's fine. So then we end up with this, which has the very fancy name, T-shaped.
Oh.
It's shaped like a T, right? So I don't know why the other ones had to be so hard. Anyway, so T-shaped. Any questions?
So
Yeah.
you actually had to draw out like the other ones you drew out you connected them with that one just
Mhm.
like a that would be like a triangle like just like
Well, in a sense, this is like a triangle because, I mean, you could do it like this. But there you're going through the central atom.
you're going central so you can't.
Yeah. So that's different than the trigonal planar,
Okay.
where when you make the triangle, you're just connecting the atoms, the exterior atoms.
Okay.
Yeah. Okay, so let's talk, oh wait, one more. So here we've got 5 electron groups and 3 of those are lone pairs. So again, 5 electron groups, trigonal bipyramid, lone pairs. we're gonna take them off the equatorial position where there's more space, or think of, it's better to cut off some of her tutu than take off her head, right? So here we have now her tutu's gone, and that is linear. Questions? So you can get linear in more than one way. Okay. Now with the 6 electron groups. I'm going to switch central atoms here. So 6 central atoms. 6 groups. 6 balloons make an octahedron. Now, where we put the lone pair doesn't matter because all the angles are the same. So you just pull one of them off. And then you can look at this however you want. Somebody last night said, well, that looks like a Joy-Con. Okay,
And it
it does look like a joystick, right? But all these terms came up way before things like that, so we're going to stick with what they call it. So they call this a square pyramid. So this is a pyramid where the base is a square and it comes up to a point.
Isn't that what real, like, real?
Yeah, this is, the Egyptian pyramids are going to be like that. Maybe not that wiggly though. Square base, as opposed to the trigonal pyramid, which had a triangle base. This has a square base. Okay? What if we have a compound with one more lone pair? Well, now we do need to consider those. We've got 2 lone pairs. Where are they going to be relative to each other? They want to get as far away as possible. So it's going to be on the other side of the first lone pair. And that is square planar. It's square and it's flat, which is what most of the Lewis structures look like, but they're not trying to represent the shape. So this is square planar because these would go on opposite sides. This is a table from your textbook which summarizes all of these different things. Imagine a molecule with 6 electron groups that are confined to 2 dimensions and therefore has a hexagonal planar electron geometry. If 2 of the 6 groups are lone pairs, where are they located? So they're saying that this is a flat molecule. So just as it looks, it's flat, and we're going to have 2 lone pairs. So if this is one of the lone pairs, where would the other lone pair be? It would be on the opposite side because they hate each other the most. So it would be positions 1 and 4. This is a nice summary slide. Which statement is always true? The shape of a molecule is determined only by repulsions among bonding electron groups. Whoops, that's not what I thought I had. Bonding electron groups. Determined only by repulsions among non-bonding electron groups. The shape of a molecule is determined by the polarity of its bonds, or by the repulsions among all electron groups. It's going to be D, right? It's all of them. A can be true if you have no lone pairs, right? If there's no lone pairs, then it is determined by the bonding pairs. But if you have lone pairs, they also come into play.